All right. All right. So, all right. Welcome back, everybody. This is the final exam review for 1202. My dog is playing with her toy, so she's being kind of annoying right now. So hopefully you guys can't hear her. But I just wanted to go over the first midterm review and second midterm review real quick before we jump into the final review, because I kind of wanted to just brush over all the stuff that we've went over this semester, because majority of this stuff is already on YouTube, on the IEEE YouTube for UTD, and I went over most of this stuff in the first midterm review and the second midterm review, but kind of wanted to just touch base so you guys can get a quick refresher. I don't want to spend too much time here because there's a lot of stuff to talk about, but let's just scroll through this real quick and talk about a few things. So I'm not going to talk about all this. Oh, and by the way, real quick before I go on, I'm going to upload all of these reviews, midterm 1, 2, and 3 to the IEEE Discord after I'm done. So anyways, let's move on. So yeah, let's go get started. So we know about Ohm's law, obviously. I'm not going to go into all this detail. Power, we know about that. Kirchhoff's laws, you guys are very familiar with this by now. The sum of all currents going in must equal the sum of all currents going out. KVL, same thing. The sum of all voltages must equal 0 in a circuit. And in the first midterm review, I did this problem on the video. And so I'm just showing it here in case you guys want to have some additional practice, kind of work it out on your own. But I'm not going to go through this again, but you know, this is just a simple KVL, KCL problem. So series and parallel components. Obviously, we have our series resistors. This is the equation. Parallel resistors, this is the equation for it. And then this is a little shorthand for parallel resistors, which I went over in the first video, which is really useful, but not necessary. Series inductors and parallel inductors are the same formulas as resistors, and series capacitors and parallel capacitors are the inverse as far as the equations go, or the opposite as far as the equations go. And this was an example I did on the first video where I just kind of showed why this little notation, this shorthand, was useful. I'm not going to go through it right now, but it's pretty useful, kind of just giving you guys a refresher. And here's an example of why that's useful, because you can collapse this entire resistor network to find the equivalent resistance in one line, essentially. Okay, so here's the voltage divider circuit. You guys should be familiar with this by now. I did a voltage division problem in the first video and the second video, so that should be pretty well covered. Current divider circuit. I don't think this is actually necessary for this course, to be honest, but it's the same methodology as the voltage divider circuit, to be honest. It's just a few different variables, or moving around a few different variables. Yeah, it's pretty simple. And you're finding current instead of voltage. We did this problem. This was the voltage division problem. Pretty simple stuff. Okay, so let's start here, I guess. So sinusoids, we know these by now. This is in the time domain. This Vm is the maximum amplitude, and then this omega is the angular frequency, and the phase is phi. Omega can be represented by 2 pi f, which is in radians per second, or and to convert that to frequency, or to convert that to hertz, you would use frequency, which is omega over 2 pi. And here's the same thing for seconds to hertz, hertz to seconds. Here's an AC wave waveform, and we went over that. I didn't really get to talk about this last time too much, but I don't really want to get too much into this right now, but I kind of want to, I guess I just will mention a few brief things. So basically, when I was taking this course, I was getting caught up on, I I was having trouble with how there's so many different domains and so many different planes. You know, there's the rectangular plane or domain. There's the polar domain. There's the phasor domain, the complex domain, the frequency domain. There's all these different domains, and you kind of just get thrown into them, and you don't even know where you're at, right? So, just wanted to briefly mention this is like the real and imaginary. So the real would be the x-axis, and the imaginary would be the y-axis, right? So when you're in this domain, you're in the complex domain. The complex being the real part, or the x-axis, and the imaginary part being the y-axis. And you can see that represented in Cartesian form by x plus jy right here. That would give you, if you charted the x and the jy coordinates, you would be in the Cartesian form of this domain, this complex domain. And equivalently, you could also stay in this complex domain, which is still real, still imaginary, but instead of using x plus jy, you could use r theta, right? And r theta is just your polar form of this same domain, which this domain is the complex domain. But one thing I wanted to mention is there's also the phasor domain, which is just not really a domain. It's just a phasor is just the same thing as polar, essentially. But they renamed phasors so that engineers could sound cool. Phasors literally just mean a vector in polar form. It's literally the same thing. So polar is equivalent to phasor. These are the exact same thing. Phasor is engineering specific. It's like only engineers use the word phasor, right? Because they're like, oh man, we're so cool. But they're the same thing. And then there's also the I already talked about the complex domain. There's also the frequency domain. And one thing I want to touch on is the frequency domain is not the same as the phasor or the polar domain. The frequency domain can only be accessed by taking the Fourier transform, which is something you might have used or may have used or heard of, but maybe not. I didn't hear about it for a while. But to get to the frequency domain, the only way you can get there is by taking the Fourier transform of a function that's in the time domain. So, for instance, well, not for instance, that's just a fact, but let's just talk about this real quick. So phasors have this omega, right? And an omega is an angular frequency. So whenever you've been working these problems all semester long, omega is always like 20, 50. It's just like one single value, right? That's because the phasor, where's that? Yeah, because a phasor is a complex number that represents amplitude and phase of a sinusoid, right? So amplitude and phase. So there's no frequency. There is a frequency component hidden inside the phasor, but it's for one singular frequency. So whenever you work out these problems, omega is always 10, omega is always 50, and you're able to work out the problem successfully. But you're using phasors in this complex domain. You're using phasors in this domain, right? Because this is a phasor, this is a polar, they're the same thing. You're using them in this complex domain. But the frequency domain, you are not on the same axis, or you're not in the same domain. So the frequency domain is omega and then x omega, which is, this is the frequency domain. This is not the complex domain. And I'm going to get to the point to where I'm trying to make here shortly. But I just wanted you guys to know this because there's all these different domains and all these different planes and stuff like that, and they're very confusing if you don't really know all of this stuff. So the frequency domain, when somebody says that, you need to be making sure that you're talking about the same domain, because a lot of people think that phasors, because they have a frequency in them, that they're in the frequency domain. They're not. They're in the complex domain. And even though the phasors have one singular frequency attached to them, that's how you're able to work with phasors, is by using that one. You're able to solve the circuit for that one particular frequency only. The frequency domain has multiple frequencies throughout here. Anyways, I just wanted to briefly mention that, and I hope I didn't confuse anybody. Let's move on. Yeah, so you guys know all this. Phasors. Yep. Operations. Okay, we did go over this stuff already. Impedances. I didn't really get to work out a problem with this, but I know you guys have probably done quite a bit by now. But I am going to try to work out one this video, hopefully by the end of it. And then we talked about complex numbers, and yeah, so that's just a brief review of the first midterm review. Second midterm review, I'm just going to grind through this real quick. It was over ideal op amps and filters. Yeah, so let's just skip through that. Okay, in the second video, I talked about the inside of an op amp and the reason why ideal op amps work the way they do and what's actually going on in here. So if you didn't get to catch that and you want to know, just go watch that video. And then let's talk about this. So this is inverting amplifiers. You just need to know these two formulas, and this is just what the input and output waveform look like from an inverting amp. Non-inverting amp, same thing. Here's the formulas. Here's the input and output waveform. Summing amp, here's the formulas. Difference amp, here's the formulas. That's all you really need to know about that. In the second video, I worked out this op amp problem and kind of indirectly proved that this formula was accurate. So that was kind of cool. Excuse me, let me take a drink. Okay. And also in the second video, we worked out this problem. So the reason I'm showing you guys all this, because somebody might just be tuning into the final for the first time and they haven't seen the first or second review. So I'm just giving them some quick little pointers if they want to go catch up on this stuff, and they like, man, this final review he just rushed through everything. There's a reason why. But anyways, so we're going to talk about filters a little bit. We talked about this in the second video as well, but this is just a brief overview. You know that filters are just meant for passing or amplifying certain frequencies while attenuating other frequencies. This is the graphs of these frequencies. So obviously the low pass filter, as the name implies, passes low frequencies and blocks high frequencies. High pass filter, as the name implies, passes high frequencies and blocks low frequencies. And excuse me, the band pass filter is a single band of frequencies that it tries to pass only. Yeah, so we talked about all this stuff. Here's a few quick definitions for you guys. These are pretty useful. Okay, let's talk about this real quick. So this is low pass filter, what it looks like. Here's the impedance ZF of the low pass filter. And here's the equations you should know that are associated with low pass filter. High pass filter, here's all the equations you should know. Here's the ZI, which is the impedance part of the high pass filter. And band pass filter, here's these equations you should know. And all of the decibel equations, which are pretty useful for this exam, I believe. I believe there's a lot of, when I took this exam, I needed to know these for sure. Okay, and then we worked out this problem on the second video, so just briefly touch on that and this one. Okay, so let's go to the final review. Excuse me. Okay, so this is the final review, and before I talk about the final review, I just want to mention how this exam went for me, and why it's kind of just is the way it is. But this final exam, if I remember correctly, it was a lot of like memorization. So I don't want to bore you with just going through sample slides and like just reciting off all these monotonous stuff about the slides. Like I feel like, if you're here, you're also going back and looking at these slides too, so you can review those slides. Those slides are great. They have a lot of useful information in them, but I don't want to bore you with just going through slides. So I'm going to try to go through some stuff that I think is important for your future, and stuff that I think that is important for you to know, and maybe try to work out a few example problems towards the end. So let's just jump right into it, because a lot of the stuff is a lot of memorization. Also, I've been saying that, but what I'm getting at is you should go back and look at these slides and study the key phrases and the stuff that she mentioned that you should memorize for the exam, for this final exam, because that's the majority of it. Anyways, let's move on. So I added this to the final exam. This is from my current class, which is in Signals and Systems, and I kind of just wanted to add it because I thought it was kind of useful. But basically, this is saying how a RC circuit frequency response is typically reported, which is a Bode diagram. And I know you guys have been familiarizing yourself with Bode diagrams, and so I kind of wanted to just briefly do this. So let me just read the top up here. Instead of plotting HJ omega, and HJ omega, you can just kind of ignore it, but it's just basically saying you're in the time domain. I'm sorry, not the time domain, the frequency domain. Engineers prefer to plot the magnitude of HJ omega squared, which is more informative because it tells us what happens to the time average power if the signal is periodic, or energy if the signal is aperiodic, meaning non-periodic, of the signal as it traverses the filter. In addition, considering that the significance of the signal received as it is perceived by our auditory system is proportional to the log of the signal power/energy, engineers have introduced the decibel unit, decibel dB unit, which is this formula right here. I know you guys are probably been using this one here. And this one's just equivalent, but it's just manipulated with logarithmic algebra, to get this one. They're the same thing. But yeah, these are pretty useful. And this HJ omega, you can, for all intents and purposes for your class right now, you can replace this with gain, or voltage out over voltage in. And anyways, so this is the Bode diagram, which you guys know. Here's the negative 3 dB cutoff frequency, and this is the slope at negative 20 dB per decade, and the slope indicates the selectivity of the filter. So if you had a slope that was negative 40 dB, for instance, it would cut down even further, and it would be a sharper slope, and all of this would basically get cut off. It would just make your filter more selective, right? Let's see. And so this is interesting because if you look at this function, right here, this is what it would look like with a regular linear scale on your x-axis. So you can see why the Bode diagram is so useful, because you can really zoom in and see what's actually happening. It would be hard to analyze these upper portions right here. But yeah, I just wanted to mention this briefly because I thought it was pretty interesting to know why Bode diagrams are used, because like it says here, time average power or energy as it traverses through the filter is easier to identify. And that also makes sense because once you start learning about Fourier transforms, you're going to learn about power and energy in the frequency domain. So that's very useful. All right, so let's keep going. So sampling, yeah, so sampling is basically a part of the analog to digital conversion process. So it's used to convert continuous time signals, which is analog, to discrete time signals, which is digital. This process is used in many digital systems, such as microcontrollers, microprocessors, other digital integrated circuits that perform operations with binary data. So I kind of want to just draw this process out for you guys real quick. Just so maybe we could kind of see what's actually happening when you convert analog to digital or analog to binary, because basically there's a ton of slides you could look at, but it's kind of like very long and drawn out process through the slides. So I kind of want to just do a really quick succinct version of that. So let me just draw it here. So say we have an analog signal, and we're going to draw it right here. This is time. And this is a function with respect to time. This function could be v of t for voltage, I of t for current, but I'm just going to say x of t because it's just a generic function. And then let's just draw just a random signal. That was terrible. Let's do that. Okay, so one thing we should note about this analog signal, this is just a random signal I drew, but this is in continuous time on the x-axis and continuous time on the y-axis. So how do we convert this analog signal that we got from, say, sound or temperature or light or heat, or as I said, heat, temperature. You get what I'm saying. It's just an analog signal, right? How do we convert that to binary data? Well, the first step in the process is going to a sampler. Okay, and the sampler is basically, like we just described, converts continuous time to discrete time signals. Discrete time signals, not necessarily fully digitized yet. That's important to note, but let me draw it and show you why that's the case. So let me just draw this. So this is time. Okay, so let's try to replicate this little signal over here onto our axis, and I'm just going to draw some dotted lines because, and I kind of zoomed in a little bit, but these are not data points, by the way. This is just me trying to recreate this analog signal on, like, superimposed onto this graph, right? I'm not trying to make these data points. But so the first thing to do is we want to sample this signal, right? This analog signal. So what a sampler does is it takes little samples all along this analog signal. And let me just draw these real quick and I'll explain. Okay, so this is TS, and TS, and this is the origin 0. So at TS is the, let me write it here, TS is the sampling period, and this is the sampling period of this analog signal. So basically every interval of TS, you would take a sample of this analog signal. So this would be 2 TS, this would be 3 TS, 4 TS, and so on, right? But this is not the actual output waveform. The output waveform looks like this. It goes up and samples right there. Well, it takes in this whole strip right here is considered, you know, one piece of data, right? It's just how we have to draw it on the graph. So this is what the output waveform of the sampler looks like. Okay, And let me just draw this real quick too. So this distance right here to here is TS, right? And you'll notice that all of these little values have little amplitudes going along here. One's there, one's there, one's there, one's there, one's there. All these little amplitudes are running along there. The amplitudes are in continuous time because there's infinite amount of amplitudes that it could sample. But the x-axis is actually in discrete time. And so that what that means is that you converted the continuous time signal, which is an analog, to a discrete time signal, which is still in the continuous domain, but it's now in discrete chunks. So you have these little discrete finite amounts of this continuous time. So what that means is you haven't fully converted this to binary, right? It's still in continuous time and it's not usable. So the sampler needs to do something else. And that something else is going to what's called a quantizer, which you guys are aware of. And the quantizer is the device that truly turns this semi-continuous output waveform into discrete. So let me draw the final graph of this. It's going to be looking like this. And you can consider this to be n and x of n, because this is n for discrete, x of n just means you're in a discrete time, or you're using discrete values, I should say. And so real quick, the quantizer works with a number of levels, right? So there's 2 to the n number of levels in a quantizer. So let's say we want 8 levels. We would have to use n is equal to 3, right? Because 2 to the 3 is equal to 8, right? So let's do that for this, just because that's really all I could fit here. So let's do one of these. Will be like that. Let me just draw these real quick. Hopefully this will be worth it. Okay, so I didn't count, but let's see, this is 0, 1, 2, 6, and 7 up there. Okay, so let me try to recreate this this graph. Let me superimpose this waveform on top of this quantizer graph. So what it's going to look like, I'll just do the best that I can here. So let's go up to here. There. I think I've already messed up, but you get the idea. Let me just draw these real quick. Okay, and actually, now that I think about it, this waveform at 0, this waveform starts with a value already, so it's technically like this. So I should do that over here too, actually. Okay, so the quantizer, this is the graph of the quantizer, right? So this is how we can turn it into completely a digital signal, a fully digitized signal will give us values that we can turn into binary data. So what it looks like is this. And notice you don't have to go all the way to the dot. You remember these are in between values, right? So each one of these levels, these dotted line levels, is the value that is getting read by the quantizer, not the actual dot of the signal. So you just have to go to what you think is closest. Oh wait, nope, I messed that up. So let me try again. This is a little bit hard. Okay, let me go see. Something like this. Okay, so this is what the quantizer would produce. It would produce a fully digitized signal from this analog signal. And you would think that you'd be done right there, but you're not quite. It's almost done. So the last step, which you might already be ahead of me, is the encoder. Erase this. So that would be the encoder. And let me just grab this real quick. I don't think I, damn it, sorry. I just need to make some space. Okay. Okay, so this would be the encoder. And the encoder basically converts all of these values that the quantizer produced into binary values. So then it turns into binary data. And so everything in here is considered the analog to digital converter, right? So these are all part of the analog to digital converter process. The analog signal, you start off with the analog signal. This is what it looks like. It goes in, goes to the sampler. The sampler is the device that does all of the filtering. And the sampler produces this graph, which is continuous time in the y-axis, discrete time in the x-axis. And then you go to the quantizer afterwards, which is produced by 2n number of levels. And that's set based on the number of bits you want your ADC to be, your analog to digital converter to be. So your quantizer then produces this graph or this output. And this is going to be digital time, or not digital, discrete time in the y-axis and discrete time in the x-axis. So it's a fully discrete signal this time. It's fully, they're just numbers now, not analog values. And then the encoder is basically your last step, and it converts all of these to binary. So this would be 000, 001, 010, 011, etc. Right? And that's what the encoder does. So this is all the steps. And oh yeah, your encoder is determined by n number of bits. So n bits just means however many bits you want your analog to digital converter to be. So hopefully this was helpful. I just kind of wanted to briefly go over this process because I know this is kind of like a lot, but maybe this shines a little bit of light on what's actually happening in that process. So let's move on. Sampling, we have, this is basically what I was just talking about, converting the continuous time to discrete time. And why is this conversion important? Because we can record or transmit continuous time signals using a finite number of samples. Basically what that means is you can recover using this discrete signal, you can recover all the way back to your analog signal. You can go either way. So that's really nice. Let me just briefly go over this. So the process of a sampler circuit, so what's actually happening in the sampler, not just like it goes from here to here. So what's actually going on the inside. So here's your analog signal. You got your input waveform, which is x of t, and your output waveform, which is y of t. So your input would be x of t, and this is your analog signal. It goes into the sampler. In this case, the sampler is just a switch that's basically running on a clock, and the clock is based on TS. So TS is just your sampling period, and every TS, the switch closes briefly to give you one little output. The next TS, 2TS, the switch closes and gives you another output. Next TS, 3TS, switch closes, gives you another output. And so all the other times, your switch is an open. This switch is primarily an open circuit. But for a very brief amount of time, the switch closes and gives you a small little output waveform. And that's how the sampler works. The sampler multiplies essentially this function, this analog function, by this train of unit impulses. And you'll learn about this in signals and systems. But this train of impulses is actually called the delta t function. And they multiply each other, and this is what you get in the output of the sampler. So yeah, let's move on. So the sampling theorem, basically this is where the Nyquist stuff comes in to play, and I kind of want to just briefly go over that. So omega s is the sampling frequency or the rate. Omega m is the maximum frequency of the message signal, and the Nyquist frequency is the minimum sampling frequency allowed to use to collect samples of x of t while still being able to reconstruct x of t from its samples only. Basically, all this is saying is, your Nyquist frequency is the minimum sampling frequency, and that's this, your omega s essentially, and it needs to be twice the omega m, which is your maximum frequency of the message signal. So let's look at what the message signal is. So whenever you're doing sampling, this is basically explaining why Nyquist frequency is important. So here is the frequency domain, and when you're in the frequency domain, omega is here and x omega is here, right? This is not real and imaginary. That's the complex plane or complex domain. This is a totally different thing. And remember, I said earlier, the only way to get to this domain is by taking the Fourier transform of an x of t function. So for instance, if this was your x of t with respect to time, and you wanted to get to this frequency domain, you'd have to take the Fourier transform of that function. So that's the domain we're in. And I know you guys haven't really worked with this domain, but I kind of just wanted to show you the insides of what's actually happening to the best of my ability. So this distance from origin to right here is omega m, right? So that's the bandwidth of this message signal. So this whole triangle in the middle is considered the message signal. It's the frequency that you want to pass, essentially. And so this distance from here to here is considered 2 omega m, because omega m to here, or here to here, is omega m, right? So double that would be 2 of them. And so that would just produce this other spectra. And spectra is just essentially another harmonic in your frequency. And you'll learn about that later. But this is not part of it, this LPF, which is a low pass filter, but I kind of wanted to show you what this means and what it's doing. So this LPF, this low pass filter, is just boxed around this message signal, and everything inside of this LPF is being passed and everything outside of it is being blocked. So this is called critical sampling, and that's only whenever omega s is equal to 2 omega m. The other sampling is called oversampling, and it's when omega s is greater than 2 omega m. And it's the same thing as this, but now you have this distance right here, which is omega s, which is greater than 2 omega m, because this is 2 omega m, you have 2 omega m's. And then you have this distance in the middle, which is greater than that. So omega s is greater than 2 omega m. And the LPF box around it. Omega c, by the way, would be the cutoff frequency of the filter. So this omega c could be from here to here, anywhere in between. And then the undersampling is whenever you have omega s is less than 2 omega m. And this is basically why the Nyquist frequency is important and why you don't want this to happen. So omega s is less than 2 omega m is this distance right here. And you'll notice that when it's less than 2 omega m, less than the Nyquist frequency, you get this signal starts to intrude onto this other signal, your message signal. So this is your message signal, and you have these other spectras coming in, and they're basically interfering with your message signal. And what that does, well, it's called signal aliasing, and what that does is it causes distortion in your signal that you're trying to pass. And you don't want distortion. So I just wanted to talk about this real quick because, you know, nobody really knows why Nyquist frequency is important. I know when I learned this class, I was like, what is this? But now that we started learning about it in signals and systems, I kind of wanted to just show you guys this. So that's why it's important, because or else it'll cause distortion. And long story short. And excuse me. The quality of the ADC is determined by the signal to quantization noise ratio. So the quality of the ADC, and if you'll remember, the ADC is this whole thing right here, this whole process. So the quality of this thing is determined by the SQ&R, which is the signal to quantization noise ratio, which this is directly from her slides, SQ&R formula, and then this is the SQ&R with respect to decibels. Okay, so let's move on. Okay, so this thing was on the final, and I think it still is, and you need to know it. I'm just going to briefly talk about each one of these, and yeah, so let me just talk about them real quick. So the input transducer converts input message or data into a message signal, which is electric. An example of this would be a microphone or a camera, and that's the input transducer. And a lot of this stuff, this is what I was talking about when it comes to just memory. You just need to basically memorize all of these steps. It sucks, but that's what's got to be done for this part of the final. Transmitter encodes the message, attaches message to carrier if message will be wireless. Yeah, so this is the carrier, which is only if the signal is wireless. The channel is just the medium, so it just carries the signal over the wire, over a wire, air, fiber, etc. And then the receiver is a convert signal into an output signal. Pretty self-explanatory. And then the output transducer is the same as the input transducer, but it's just opposite. So it converts that received message signal. So it converts that received signal into an output message. An example would be speaker or video monitor. Yeah, so that's pretty self-explanatory. Again, this is just memorization. So just do your best to memorize it. Nothing really I can do to help you with that. But let's try to do a few quick examples. So I kind of pulled some from when I took this class. So hopefully they're not the same exact ones still, because that would be kind of awkward and suck. But let's just do these and we'll see how it goes. So a 3-bit ADC is used to convert a signal that ranges from 3 volts to 15 volts. Determine all of these things. So let's start with the first one, the system resolution. So the system resolution is pretty easy. It's the easiest one. It's just saying The system resolution is the number of bits you use in your ADC. So in the problem, it even tells you the answer, a 3-bit ADC. So 3-bit ADC, that means the resolution is 3. Right? That's pretty easy. So the step size is, let me just scroll back up here so you can see. The step size is this right here. Let me just draw it. So the step size is this from here to here. The distance between these dotted lines, that's the step size. So the step size, and I know there's a formula for it, which is so it's and it's the y-axis, right? Let me double check. Yeah. Y max minus y min over 2 to the b, and b is the number of bits or the resolution, same thing. So this would be y max. What's our y max? 15 volts. So 15, and y min would be 3. 2 to the b would be that, so that'd be 8. Oops. So this would be 12 over 8. Okay, so this would be, what is that? 1.5 volts. Okay, so let's do the next one. Oh, wait, did I do these backwards? The number of steps. Oh, wait. Steps. I did step size. I did those backwards. Sorry, this is actually, I did these backwards. This is number 3. The step size is that, and what I showed you on the graph. That's the step size, not the number of steps. The number of steps or the number of levels is we already did that earlier, which is 2 to the b, right? 2 to the b would be, for this case, 3, 2 to the 3, because we have a 3-bit ADC, and b is the number of bits, so that would equal 8. So yeah, sorry about that loud car. I have a lot of those around here. Okay, so that would be the step size. So we got this, and then we got this. Okay, and then the maximum quantization error. So that's number 4. And that's pretty easy. You already found this, so it's just, well, I can't draw today. It'd just be half of this. So 1.5, half of that, it's 0.75. And then SQ and R. So the SQ and R, we can use this formula up here. Let me grab it. And we can use both of these formulas. You'd get different answers, but also I'll kind of tell you, this is 1, which is this is not B, this is 2 to the B, right? No, this is 2B. Okay, so this is 3 half, 2, and then 2 to the B, so 2 times 3. And then that would give you, I've got the answers here, so that would give you 96. And this is in watts per watt. So that's SQNR, but then there is the other one, which is SQNR in terms of dB, which is this other formula. Just grab that. Oops, sorry. Okay, so that would be this, and then our B would be 3. And I haven't checked this math, but the answer says it's 19.8 0.82 dB. So that's pretty much all you have to do to work these problems that seem kind of complicated at first, but they're really easy. Just follow the formulas and don't get them mixed up like I did. And here's what the graph would look like for this exact same problem. This is what the graph would look like. So let's take a look. This is just a random analog signal, but from 3 to 15. So this would be Y min, Y max, and this is your quantizer, right? Because your quantizer is what we showed earlier, which is getting these values as close as possible to these data points. So your quantizer is producing a discrete time and a discrete voltage value. So it's quantizing this signal. And the quantization error is the value that the quantizer outputs compared to the actual point of the signal itself. And oh yeah, this is step size, which I was showing earlier. So yeah, so let's do what would this let me move this out of the way. So what would this quantizer output? Okay, so this one would be 2 again, 1 0 0 1 1 2 3 4 4 3 3 5 5 6 7 6, yeah, 6 7 6. So basically you're just, you know, right where the data point is, 2 2 1 0 0 1, and you're getting the values from the in between these ranges, or in between this step size. So that's how the quantizer output works. Okay, so let's try to do a quick this is going to be a quick I've tried to pull some example problems from my homework whenever I took this class, just so we can kind of work it out, get refreshers, you know. So let me pull up the answers to this so I don't actually mess up and waste everyone's time. Or not the answers, but the values, the answer values. Okay, so here's our graph. It's or not our graph, our circuit schematic, and usually this isn't given, but I just added it on top of there. But we can tell that this is a bandpass filter from the Bode diagram, but you can also tell that this is a bandpass filter because of, well, there we go. Because of this, which is your ZI, and then this, which is your ZF, right? That's how you can tell there's two different impedances and where they're located. So so what does the graph of this look like? So here's the things we're given. So this is omega C, the cutoff frequency, omega C, of the high pass filter part is 1000 radians per second. So we have the omega C of the low pass portion, which is 2000 radians per second. A, which is negative 5.5 dB, which is your gain, and then RI, which is 1600 ohms, and then VS, which is 6 volts peak to peak, and it's peak to peak because it's an AC signal, AC source. And then we're supposed to find CI, the gain of the passband, RF, and CF. So before we start solving these real quick, just for reference, let's see what that looks like on the Bode diagram. So as you'll notice, this is A. So A is what? This amount right here is your maximum gain, and that is negative 5.5 dB on the y-axis here. All right, and then omega C from the high pass, well, that means that it's going to pass high frequencies and block low frequencies, right? So these are higher, these are lower. So that means that this right here should be your omega C HP, which is 1,000 rad per second. And then that means the opposite one right here. I'm just arbitrarily drawing where it should be, but you know, right around there would be your cutoff frequency of LP, which is 2,000. Right. Okay, so now we've identified those on the graph, just for our own sanity. All right, so let's go ahead and try to solve this. So first things first, it says we want to find CI. Okay. So number one, we want to find CI. So how do we do that? So there's a formula for CI, which is omega C HP. Oops. HP is equal to 1 over Ri Ci, right? Well, if we want to solve for Ci, you just swap these two values. You can just multiply both sides by Ci, divide both sides by omega CHP, and then this would basically convert to Ci is equal to 1 over Ri omega C. I'm not going to keep writing HP, but you get the point. And then, so what would that mean for us? Well, we have 1 over, and then we have Ri right here. So Ri is given to us 1,600. So that's 1,600 times omega C. Well, I guess I should, huh? Omega CHP. So we know which one's which is 1,000. And whatever that value is would give us CI. Let me type it in the calculator real quick. Let's see. Okay, so this would be 625 nanofarads. And let me see if I got that right. Yes, okay. So that's that. Number two, magnitude of gain in the passband. This is a formula we know, which is just 20 log of A, right? And we have A, which is the gain, right? So what's our gain? Negative 5.5 dB. So this is A volts per volt is equal to, no, is it volts per volt? Let me double check myself. No, this is A in dB and is equal to that. So that means the A dB goes inside here. So let me see. So negative 5.5. No. Sorry, I wrote that wrong. Volts per volt. That's what goes in there. So negative 5 dB, which is the gain in the passband. We know this, so that's that. That's the gain in the passband, which is negative 5.5 dB, and then that's equal to 20 log, and then we have A volts per volt, which is what I meant to write. Right? Well, we don't have A volts per volt. That's what we need, or that's what we need to solve this problem, or to get to the. That's what we need to have to find the gain in the passband. Sorry, stumbling over my words here. So we can actually do some algebraic manipulation of our own to solve this, or we could just use that formula that we saw earlier in the midterm 2, which I'm not going to go back to, but it's basically A volts per volt is equal to 10, and then you raise that to negative 5.5 over 20, and that's just the 10 and the 20 are just from algebra, and then this negative 5.5 is, you can replace this with just gain in the passband if you wanted to, and then this would be, I guess, your standard formula to convert it from dB to volts per volt. So negative 5.5, and then this would be equal to, and this is absolute value still, so so then the gain in the passband, I'm just going to look at the answer so I don't have to type this all in, would be 0.531 volts per volt. Okay. Then let's do number 3. So number 3 asks us to find RF. Can we find RF right now? Well, I think we can. Yeah, there's a formula. So gain in the passband is equal to negative RF over RI, because this is a bandpass filter, so we can use this formula. And then so RF would be equal to RI times gain in the passband. Yeah, okay, so then RF would be equal to RI was 1600, and then this is what we just found in volts per volt, by the way, which is 0.531, and then RF, the answer tells me that it would be 849.42 ohms. Okay, and then let's do number 4 real quick, which would be omega C LP is equal to 1 over RF CF. And then if we do a little bit of manipulation, it's going to be CF is equal to 1 over RF omega C LP. And for us, that's 1 over the value we just found, 849.42 times WCLP 2000 from the problem. And this, the answer says it is 589 nanofarads. And that's it. That's all 4. So just a quick little problem there. All right, so let's move on because we're running out of time. Okay, I didn't do one of these in the last problem, or in the last couple of midterms, and I had some requests to. Hopefully you guys are pretty familiar with these by now, because I remember when I took this class, I had to do these so much. I remember there was just like endless amounts of these problems. But let's do this real quick. So this is a RLC circuit, and we have an AC source, and we're supposed to find Z equivalent and the I source. The I source would be this current coming out of the voltage source, and this is the values we're given. So 5 cosine 10 to the t. So we can determine that this part right here is omega, right? So omega is equal to 10. And then that's in volts. We have R is equal to 2 ohms, C is equal to 0.4 farads, L is equal to 0.5 henries, 0.05 henries, excuse me. Okay, so these are just kind of just long and tedious. They're not really hard necessarily. So first things first, we have to find Z equivalent. And how do we do that? Well, we take the inverse of everything. So 1 over Z R plus 1 over Z C plus 1 over Z L, all to the inverse of -1, which is equal to, and I'm just going to throw the 1 on top just for easier calculations in a little bit. So that's 1 over R, because I'm not going to go through these impedances, but you guys know by now ZRs are Z of C is 1 over again J omega C, because this part right here is the actual ZC, but it's 1 over that, right? And then, oops, that's plus, and then this is plus, and then 1 over J omega L, right? Okay, so Z equivalent is equal to 1 over, let's just simplify this just a bit, 1 over R plus, if you bring this J over, 1 over anything is just whatever the denominator is, you just bring it to the top. So J omega C, and that's a plus. And then we have, so 1 over J is equal to -1, right? or sorry, not -1, negative j, sorry. And so we could just say that's negative j times, because we'd pull that out, and then that would be left with 1 over omega L, right? Okay, so Z equivalent is equal to, let's start plugging in numbers, 1 over 2 plus j, and then omega is 10. C was 0.4 minus j, and then 1 over omega, which is 10. And then L, which is 0.05. And then this is going to give us 1 over 0.5 plus J4 minus J2. Okay, and then we could just simplify this and say this is J2. And then so now we have a phasor in the numerator and something that's in rectangular in the denominator. So we need to convert this in the denominator to phasor form. So that's going to be Z equivalent is equal to, let's just do this. So 0.5 squared plus 2 squared, because that's x and y. And then we're going to have inverse tangent. It's going to be 2 over 0.5, and that's going to be our angle. And then all that is going to be over 1. And when we do that math, we're going to get 1 over 2.06, angle 75.96. Okay. And then we have now a phasor in the numerator and a phasor in the denominator. And you know that whenever you divide, you just subtract the top angle from the bottom angle, and you divide the 1 by the 2.06. So when we do that math, we're going to get Z equivalent is equal to 0.485. And then we're going to get negative 75.96 degrees. Okay. And that's going to be our impedance in ohms. And one interesting thing you can take from this is notice that this is our Z equivalent, and Z equivalent basically tells you what type of load you have, and what type of load you have basically is what I mean by that is your inductive or capacitive load. And I know she talked about this with you guys, the Eli the Iceman thing. So it's actually pretty useful. So here's L, here's C. So we have a negative 75.96 angle. So that's down here, and that's 75.96 angle. And so this is in the C, this is in the capacitive quadrant. So that means that this is a capacitive load, right? Sorry for the loud cars. They're super sweet. Okay, so here's IS. We need to solve for this, which is VS over R equivalent. And so this is 5. Because that's our VS, right? Yes. That's just 5. And then this is what we just solved for, Z equivalent. Sorry, Z equivalent, not R equivalent. 0.485. Negative 75. Can't draw today. And then when you calculate this, is going to be 10.31, 75.96. All right. So, oh yeah, the Eli the Iceman thing. So Eli Ice. So since this is a capacitive load, we have the capacitor here. So that means that this current is leading the voltage. Oops, the voltage. So voltage is written E because it's a EMF. So it's a, you know, sometimes people write E instead of EMF or instead of voltage because it's a electric field. So I leads E or voltage. So that just means the current is leading the voltage by 75.96 degrees. And what that looks like on the graph is basically, say this is your current and this is your, oh my God, it's terrible. This is your voltage. So your current would peak first. It would peak first before the voltage. That's all that means. When you see leading or lagging, you just look at which one hits its maximum amplitude first. Okay. I have one more. We can try to run through it real quick. I know I'm already a little bit over time, but this one shouldn't be too bad. But I was just trying to find like difficult problems for us to work on, or as difficult as I could find anyways. So here's our circuit. It's in DC. Here's our DC source. We have a couple of resistors, or more than a couple, a bunch of resistors, 2 capacitors, and an inductor. And this might look scary at first, but it's actually not bad because, again, we have a DC source, which, as you guys probably already know, whenever you have DC, capacitors and inductors act differently, right? Capacitors are open circuits under DC, and inductors are short circuits under DC. So with that being the case, let's redraw this circuit, and let's just try to do this real quick. So that's just a straight line because it's a short. I guess I could just draw it here so you'll know it's there. This is an open. This still have the resistors. Okay, I'm not going to draw the values, but let's just go over this real quick. So what do we need to find? We need to find V1, which is the capacitor, which is the voltage across this capacitor, the V2, which is the voltage across this capacitor, and I2. So we need to find I2, V1, V2, and that's it. So first thing I would do is understand that because this is an open circuit over here, this is an open circuit, this resistor does not matter, right? Because the current going through this resistor is 0 because this is an open circuit, there's no current flowing through it, right? So what that means is this whole side of the circuit you can ignore because of its DC condition. So this is also an open circuit. This branch right here can also be ignored, and this just acts like a wire under DC conditions. So really what you have is just a source and 3 resistors, right? Because that's really all that's there. Oh, not that one. Under DC conditions, this is what you really have. And so let me actually draw these values since this is the ones we're going to use. And this one's 10, and this one's 68. Yeah. Okay, so, well, that's pretty easy for us to find the current through this because they're all on the same exact branch. And that would help us find I2 because this is still I2. And if we find the current through this whole thing, then that would also be the exact same current for I2. So I2 would be equal to Vs over R equivalent. And these are all in series, so that's R equivalent. And then this is 60. R equivalent would just be 68 plus 10 plus 14, which is 92. And then do the math right there. That's going to be 0.65 amps. for I2. Okay, so that's pretty nice. And now we need to find the voltage across V1 and the voltage across V2 still. So the voltage across V1, let's go back up to this circuit now instead of this one, even though this is the same thing as this, essentially. But let's just look at this one real quick. So V1, well, the voltage here across this, since this is a wire, this is the same voltage here. So the voltage across this resistor has to be the equivalent to the voltage across this resistor. So that means that V1 is equal to V68, the voltage across the 68 ohm resistor, which is equal to I times R, which is Ohm's law, you know. So that would be, well, we just found this. So I2, well, I could just plug it in. You guys know 0.65 times 68, and 68 is the resistor. So that value will give you 44.35 volts. And that is the voltage across this capacitor because it's the same voltage that's across this resistor over here. Okay, so last thing we need to find, and this one's a little bit tricky, but not really, is the voltage across this capacitor. So to find the voltage across this capacitor, you could do KVL in this little mesh right here. Even though it's an open circuit, you could still do it. So what I would do is do that. So this voltage source, let's start here in the bottom and go around like this. So this would be negative 60 because it's a voltage increase, it's a voltage rise. So negative 60 plus, and then we got this 14 ohm resistor right here. So this 14 ohm resistor, instead of putting it in terms of voltage, instead of saying V 14 ohms or whatever, let's just say this is 14 times I, which is the 14 resistor, R times I, which is Ohm's law equivalent of that voltage, right? Okay, and then so next we would say plus, well, the voltage across this resistor right here, since there's no current through it, the voltage across this resistor doesn't matter. It's not, there is no voltage across this resistor really, because there's no current. But there is a voltage across this capacitor still because it got fully charged during the DC time, during the time that it was charged from this battery. So there is voltage across it, but there is no voltage across this resistor because there's no current coming through this resistor. So this capacitor is fully charged, means it does have a voltage across it. So what that means is you would have essentially nothing here, it'd be a wire, and then you'd have plus V2, which is this voltage, because it's a voltage drop. And then that would be equal to 0, right, because KVL. Okay, so that's pretty easy. We can solve for V2. V2 would be equal to 60 minus 14, and then that would be times I, which is this current, 0.65, which would be equal to 50.87 volts. Okay, and that's everything. So yeah, hopefully this review was helpful for you guys. And what I would say for the terminology and the memorization stuff, just go back and watch all of the previous videos that I have if you need to, and check her slides out, and just remember as much as you can for the terminology stuff. You know, I know it's annoying, but yeah, it's just all memorization. So hopefully this review helped you guys out. I'm gonna get out of here. So thanks a lot.